Ja.
Yeah.
Ja.
Okay, now, first of all, let's give you the solution to the assignment. How do we build a parser for floats? Now, as a way of recap, remember that a grammar is typically a bunch of rewrite rules where we have a symbol, or in some cases also a string of symbols, arrow, and then a string of symbols. Okay? Now, the simplest grammars of all are those that for every traversal of the arrow, because we kind of traverse the arrows, we eat up a single concrete symbol in the final string. So, if we want to have floating point numbers, we could say that we either have 0 followed by the dot state, and the dot state is going to read the dot followed by the number followed by the s, or s is going to go into, for example, 1 followed by dot. Wow, that is too soon, because we don't know how many digits we have to process. Yeah, and another digit, and then another digit, etc. So why not just go on with s itself? And then no, I can't have multiple dots, because if the dot doesn't go back into s,
now we can only have 0 point.
and so on until 9s. Okay? Now we have, so what is this thing going to generate then? Either a 0 followed by the dot directly,
Or a number, then a 0, then a dot.
or a number,
The 0 and the dot. So then you have 10 dots.
Can't make
10
one dot.
dots.
wait a second, yes, I know, we're getting there, but so far it's not done. So I'm going to put a bar here, such implying that there is going to come more later. Okay? But with these rules, what we're saying that either we begin with 0 dot, which kind of makes sense, so we're handling the 0 as a separate case. If we choose this way, we have a 1, then what do we have?
Another s. So
Another s.
number.
So what can I also have?
Another number after that one, or
Another number.
or a 0 dot.
So I can have 1, 2, 3, etc. until the 0 dot. But actually this doesn't count so pretty out. So you know what?
That doesn't work.
No, it is too long. So in the interest of brevity, I'm going to give you the sucky one that can also have lots of leading zeros. Okay, so let's assume on the other hand that we have done this. Alright, now 0 followed by dot, or 1 followed by dot, etc. until 9 followed by dot. Yeah, sorry, I did suddenly realize that that would become longer than I have an intention to do. So now we have the first row allows us a chain of numbers. We have 0, 1, etc. followed by s itself. And s itself is going to potentially put yet other numbers. So the s so far allows us a sequence of how many digits?
Infinite.
Potentially infinite, as many as we want, okay? But is it ever going to be as a null sequence of digits?
Could be.
No, because to go to the dot, I need how many digits at least? 1. So I could go directly from s to dot, but there needs to be a digit in front of it. So we're not supporting numbers of the type dot 3f. Okay? Alright, so we have a potentially infinite, an unbound sequence of digits guaranteed by the first row. Then the second row guarantees us that there will be at least one digit followed by dot. Okay? Now I'm calling it dot, but it should be just one single capital letter, but I think it's slightly more readable. Now, what does the dot read? It may come as a surprise, but the only thing that the dot does is it reads a dot followed by,
Decimals.
sorry,
Decimal numbers.
a decimal number. Yes. Can I use the S again?
No.
Why?
You get several dots.
Because otherwise I get several dots. So I'll have a natural number, nat. And then nat is going to look very much like that, right?
Yes.
So it's going to look very much like that, but with one difference. So it's going to be 0 followed by net, 1 followed by net, etc. until 9 followed by net. Or
0 followed by F, 1 followed by F.
0 followed by F, etc. until 9 followed by F. And finally, what does the F parse? It parses an F. Alright? Now, the opposite problem, so this is the language that generates floating point numbers. Now, how would we parse this? How would we write a program that reads a sequence of numbers only as long as it has been parsed by this language, as it has been generated by this language? Hello?
Thank you. Hey, it worked.
Ah, okay. So, no, I'm going to need another one. Yeah, ignore the presence of Python, please. Float parser. Now, I do want to hear your participation. I have a string, or actually I have a list of characters, let buffer, which is made up of 0, followed by 1, followed by 2, followed by dot, followed by 3, followed by f. Okay? This is the list of characters that we have. How are we going to parse this list of characters according to the grammar before?
Create states.
I can create states. But what is the role of a state? Think about it for a second. The role of state S was to read one character to make sure that it's either 0 or 9, and then recursively call either S or the dot. So, let's define the recursive function S. What is the recursive function S going to do? It's going to take as input a list of characters, which is our buffer, and what does it look for? What does S look for? The characters it can handle, right? So which characters can it handle? Indeed, the digits, only digits.
And the point.
And the point. If it sees the point, should not have done that. Ah. Okay, so let's look at this again. So the digit, if it finds a digit, then it knows it will have to continue either in S or in dot. Right? When does it know it will have to move to the dot?
If there's a dot.
If there's a dot. So if there's a dot, we know we'll have to move on to net. So actually the dot state is a bit superfluous. We have it in the grammar, we don't need to implement a dot function. So the S function itself, the moment it sees a dot, it can continue to the next. But the problem is that S needs to ensure that there is at least a number in front of it. So we begin in S, but when we find a digit, we don't know what the next character is going to be. If we find the digit 0, then where do we go? What is the next state? Is the next state going to be S, or is the next state going to be dot?
Depends on the next character.
It depends on the next character. So how do we solve this?
Take them apart.
Sorry?
Separate them.
I could separate them, or I could look at the coming two characters. So instead of looking at the coming character, a very simple shortcut is that I simply check the next two characters. If the next two characters are a 0 and a dot, then the next thing I'm going to parse is going to be
Not.
is going to be not. If it is a character, if it is a number and not a dot, whatever else, then we read the number, and then I go back to S itself. Okay? An alternate formulation would be that S goes into a new state, which is implicit here, which is S or dot. So we go from S to S or dot, which is a state that runs S and dot in parallel. Because if you think about it, if we find a 0, what is the next state?
S or dot.
S or dot. So we could create a state which is literally S or dot.
Yes.
Which is very straightforward actually. So we can translate this directly. If there is ambiguity, then we merge states together. And the state S or dot will have all the rules of S and all the rules of dot. If S or dot finds a point, then it knows that the next one is not. If S or dot finds a digit, then the next state is going to be S or dot itself. Which of the implementations are we going to build? Well, calm down, people, calm down.
Look ahead.
Okay, so look ahead gives you a stronger hardware. Good, good. It's also simpler to implement, so I'm kind of happy about this.
Relation.
Yes, thank you. So, okay, I'm gonna match the buffer to see if it begins with what? A digit, yes. So D followed by, digit, followed by the dot, followed by digit. We want to look that far.
No, the rest of
The rest of the buffer. So buffer 1. Okay. When system.character.use digit. This is pure laziness. And what else do we want? That the dot is I can actually put it here. So it's only going to match if the second element of the list is a dot and the first element is a digit. Okay. So in this case, well, I have the digit. I could print. We have a digit, and I'm going to put it into a new line. Or we have a digit in state S. Okay. Then, how do I process buff1? Do I use S itself?
Go to net.
To net. So I call net on buff1. Then I'll have to define net of a buffer. So list of car. And net is going to fail for the moment. So assume that net is capable of doing what it has to do. Yes. Now, the next case, the next thing we can handle from S. It is a digit followed by yes. So how do we handle that?
You just go back to your
Yes, I go back, but with what? So is it correct to say that I have a digit and then something else I don't know? So the only thing I look is the next step. Either I find digit and a dot, then I know I have to go to net, or I find a digit followed by, or a dot. No, sorry, or a digit and dot, yes. So just digit and buff1 is enough. Yeah. And in this case, we have a digit in state S, but how do we go further? We go back to state S. How do I go back to state S? S of buff1. Okay? So I'm simply saying, okay, S process buff1. What if I have any other case?
You have
Or-
something you can process.
I have something I cannot process. So I'm going to say fail with cannot parse string buff. Now, how do we process net?
It contains a digit.
No, it's the same as
At
S,
least.
only you replace the point right now.
So, is it the same as this one?
No, you got bridge.
Yeah. Yes.
So what does net do?
The same as S. But
The same as S?
Except for that.
Except for the dot, yes. So, we could have a digit followed by a bunch of stuff. Oh, sorry, match buff with. And in this case, what are we going to print? We have a digit in state net. How do we proceed then? Net 1. Net buff 1. Good. So, a question is, when do we stop? When?
We get an F after this.
When we get an F after a digit.
So it's the same as the point of view.
So-
F is on.
It is going to be to kind of like this.
Yes.
Yeah, only the last line.
Only?
The last line is different. Because you have to stop and not go to another state.
Yes, but
And
it's
you
also
look for
not
an
with a dot,
Yeah,
but with an F. Okay. When the first one is a digit, then we have the final digit in state net. And then what do we return? Nothing. We are done. Okay? So this is just to print what we have recognized. What do we require of buff1 at this point?
white space.
Sorry?
White space?
White space? That is brutal. What would we ideally want?
End of file.
This,
Different than.
and then the end of file. So the end of file is going to be which kind of list?
Empty one.
Empty. So I am asking, I do not want to accept garbage, trading garbage, okay? And in this case, on the other hand, yes, we go ahead. Any other case? We don't know what to do.
What happens with the empty sign? What happens if you don't do that?
So this one,
Yeah.
if I put something like this,
No,
Then
if you go back to the buffer, what happens? Like you had it like that, what happens then?
Oh, you don't do anything with it. So
I don't do
it's
anything
just
with
there.
it, but since I'm giving it a name instead of specifying that it's the empty list, what I'm saying basically is, as long as I find the F, I don't care what's after.
Oh, okay.
But I want to give an error if there's like an F followed by an X.
Yeah.
Okay, I don't want to accept weird stuff. I want to be very conservative. So now I'm going to call S on buffer and see what happens. Oh, okay. It works. After all, it's always a nice surprise. Now, bigger, yes.
There we go.
So we have a digit in state S. 0, 1, 2, then we have the final digit in state net, and finally we are done.
We're getting the dot.
No,
Now you're
we
not printing it, but
are not printing it. You want me to print that we have the dot?
But
no,
we
just
had a 4. Oh wait, that's it.
We forget a piece.
Oh no, yeah, the F and the
the
dot.
F and the dot.
Okay,
You're
okay.
okay.
We have a digit in state F. We have the the dot, and we have the F. Alright?
The F word.
You have to be really correct.
Alright? 0, 1, 2, dot, 3F. Okay? So obviously, instead of printing, what we typically do is we define a token data structure, and yeah, we basically just return a list of tokens instead of just printing out what we found. But I'm not going to do this now.
If we change it to a double, we can say we have to be.
Yes, I know. That was my thought actually. I thought I'm not gonna say it this time. And yet I'm saying it. Alright. Yep. So now, as you might have guessed, this limitation for type 3 languages is actually quite constraining. So this is quite a weak way of expressing parsers. Just eat the first character and then you know exactly what's going to come next. It is very limiting. Type 2 languages are the natural extension of type 3 languages. They are quite more powerful in the sense that they support the rules of the type non-terminal goes into gamma, where A is non-terminal. What are non-terminals?
States.
All the states we support. So all the things that can be further expanded. Gamma is a string of terminals and non-terminals. Notice that gamma is a string of terminals and non-terminals. So one state, how many states can it generate? If gamma is a string of terminals and non-terminals, and we just said that non-terminals are kind of states,
It depends how much you put in there.
then exactly, gamma can generate
Potentially.
not potentially infinite, never potentially infinite. We don't know how many, an unbounded number of states.
One day you can say
Potentially
that.
fine.
One day you can
Always
say
fine.
it's infinite.
What gamma can also contain is also a bunch of non-terminals. What are the non-terminals?
Here's the next state.
They are whatever symbols we were given. The terminals are the concrete symbols. In the case before, in the type 3 language before, which are the terminals and which are the non-terminals?
The non-terminals are not and S.
And F and dot. So S dot, not, and F are the non-terminals. What are the terminals?
There's no first.
Anything that's a car.
The small F.
Yes, so 0, 1, 2, 3, etc. until 9, dot, and F. Okay? So the terminals are the actual symbols that were given to you. In the case of the type 3 language, typically these are the characters from the file. In the case of the type 2 languages, whatever the previous parser gave us. So they probably will not be characters, they will be data from a data structure. So an example of a type 2 language might be something that reads up arithmetic expressions. So S can be, oh wait a second, no, this is cute, parenthesized expressions. So a parenthesis followed by S itself, followed by a closed parenthesis. Or square bracket followed by S, followed by square bracket. or curly bracket followed by yes followed by curly bracket, or the string hello. Now, to make stuff slightly more fun and interactive, you have 5 minutes to do a derivation to show the full derivation of this for a sample of your choice of at least 3 steps. Then I'll call someone randomly to do it on the at the smart board.
I'm sorry, I don't understand.
Yeah.
Okay, guys. And you may pick a second student to assist you.
What? But I thought the assignment was to do it yourself. Oh, must I then just take what I already written? Or?
Yes.
Okay.
Wait a second. Where did the quotes come from?
The quotes come from this S.
S does not support quotes.
Oh! We have to use that.
Apparently.
I did not understand it completely, so that's why.
Yeah, exactly. Just change the quotes.
So the string is also has to be the same. That's boring.
Yeah, so sorry that the entertainment of the lecture is not of a high enough quality. So the point is, you're always going to be expanding the innermost, right? So the brackets, the first brackets are actually the last ones. Thank you. Okay? Yeah. No one said this was going to be hard.
It's gonna be weird.
Imagine now that I want to parse arithmetic expressions. So, what kind of arithmetic expressions will we parse?
Unicorns.
Can you make me an example of an arithmetic expression?
3 plus 5.
3 plus 5. Can you make me an example where the second addendum has brackets and a multiplication?
5 times 2.
Thank you. Okay. Now, what shape can such an expression take? I mean, this is S, this is our expression. Okay, let's make another bunch of examples. This is a valid arithmetic expression. This is a valid arithmetic expression. Right? This is a valid arithmetic expression. So all of these expressions, what do they begin with? What does the first one begin with?
The digits.
Sure. Only because it's on the left. Sorry?
Evaluation of the arithmetic expression.
Yes, but the first expression, what is it?
The times is the first thing you're gonna do.
Are you sure?
That's O.
Plus is the first one.
Because it starts.
Because this one is an addition of two things. Now the fact that one of those things is a multiplication, and that you first need the result of the multiplication.
Yeah, you have to start at the, if you're normally
No,
calculating, you have to start at
exactly.
the other two.
You start up. So what this is it's a sum,
Yeah.
right? So this is a sum of two things.
Yeah.
And what are these two things?
Have to do in a multiplication.
Are they also?
Some of two are arithmetic.
You scream that, please.
2 expressions.
It is the sum of two expressions, right? So an expression can be the sum of two expressions. Let's look at the second. What else can it be?
Times. So expression times expression.
The second. Oh, the second. I mean second row.
Just an expression. Just S.
Just
S or just a number.
just a number.
Yeah.
Int.
Yeah.
Assume that int comes from a type 3 language that we have defined before, because now we know how to define it. Or, what else is it?
S times S.
S times S. Or we could also say
S1.
S within brackets, because we do have the brackets there, so we might want to support the brackets to change the order of evaluation. So we might very well be able to say 5 times 3 plus 1, so the brackets are actually important. And then we can have or S minus S, S divided by S, and so on. Right? This is an expression. This is a very simple arithmetic expression evaluator. Now, I will ask you to think for a second about how this will be generated by that language there. Generate this from this. So we start. I'm going to use blue. We start with S. Then we go into
S times S.
That's just an expression, so that could just be S as well. It depends on so S goes into another S. This is the start.
we are doing 5 times 3 plus 1.
5 times 3 plus 1. Or 5 is. This is 5 then?
No, it is S. So this is the whole expression.
Yes.
Danny?
Would be
Also,
another S.
Yes.
Would you assist?
S times S.
So, but S times S is already a part of S.
It is a defined state, but you need to 5 times 3 plus 1. You need to put them together into the stage.
Yeah. So it's just S times S.
Yes.
Because S is already 5 in the times, and the other S is 3 plus 1.
Yes, exactly. So pick
So-
one. It doesn't matter which one you pick in this case.
So this one goes into.
Underline the one that you are going to expand.
So that
The
one.
second, okay?
And that's S plus S.
Ah, be careful.
Very good.
You're
Yeah.
expanding the whole state.
You're expanding the whole sentence. So if you have S times S, guys,
You know, S times and then
what you will get is S times and then whatever you expand for this.
otherwise it's not correct.
Which is S times, nah,
That's S plus.
No.
no, it is S times and then the expansion of the second.
And that one is S plus S.
And the second one is S plus S.
Yes.
But you are removing a piece of the expression which is still there. So what you get is S times S plus S.
Yeah.
You're eating up the first S.
Yeah, you're forgetting the first S.
Get out, go ahead.
Jullie, je moet ook erbij schrijven.
That's correct.
Yeah, no, but
Oh, you want to expand the first one? Nah. Now we are really killing it.
No, now you're saying that that S is 3 S's. And that's the whole expression.
yeah, there's one Z here. You need to keep this here expanding.
Let's take a step back.
I know.
Yes.
Ja, die komt er en dan één ding.
Ja, de expression is
Guys, wait. Let's remain in play. Okay, so S times S, then we expand the second, and then we get S times S plus S.
Aren't you formally skipping one step now?
No, we are not, because we are expanding the second. It is correct.
Oh!
Oh, yes.
You don't have to marry.
Haha. As a matter of fact, you are skipping one step because the second S has brackets. So if you want the brackets, the next step, so the first step is S times S. The second step is S times brackets around S. Come on, do it. We delete the second. Do it.
So we extend that S into S times bracket S.
Brackets S, yes.
Yeah.
Okay, and now you may go sit. Guys, the two of you. Roman?
I don't understand it.
Oh,
Then-
I know what you're trying. Yeah.
Come on! Don't be afraid. Doesn't bite. No electric shock. I suggested it. They told me I can't.
It's a short color.
It's against the law, city laws.
Yes? So the second S becomes S plus
Really
S.
wake me up.
Yes. Underline the one that you expanded. Yes, very good. Then, which one are you going to expand? Okay.
Go.
Next line.
Next line. Second.
Okay. So the first one becomes
First one becomes.
What was it?
int. Int 5. S plus S, yes. And then the two S's become both. No, one at a time.
We skip one step.
We can afford to skip one step at this point.
Int plus int.
Yes, so just say int plus int.
You first have to do the first int, then you have to do the second int.
Yes. But we can run them, we could also, but you underline the second S please, just for the sake of precision. Okay? Thank you very much. So,
Let's go, guys.
Yay.
Goed gescrollt.
how many states are active in a type 3 language?
Shave.
How many at a time?
At the time.
In a type 3 language, this is a type 2 language.
One.
1. In a type 2 language, how many do we have?
Depends.
It keeps growing. So we have, you could imagine this to be kind of a stack of states, and all the non-terminals in the string, and you see the non-terminals keep growing. So here we have one non-terminal, here we have here, and if the expression has even more nesting, it keeps growing. So this is kind of a reminder of where we still have to do some work. Okay, this is kind of a this you could very much see this as a stack that says these are the call frames, the stack frames of the stuff that's not processed yet, which will eventually return a value that will be assembled in the final expression. All right? So it's actually very easy to define.
Sir, are you able to define priority when expanding the states?
No, you are not. You actually have to build the grammar with different. Here we only have the S. If you want some priority, then you have to use multiple non-terminals. So you can have some that expand first and others that expand later. Other kinds of things that we could process are, for example, statements. A statement in a programming language would have a grammar like if terminal bool exp, or even just exp. Is exp a terminal or a non-terminal? It's a non-terminal, obviously, and exp is the one that we just processed. If exp, then what do we have after the then? The next group of statements, which I'm going to call just a statement actually. Then what am I missing? Else. And after the else, what do we get? Yet another statement. Another example of a statement could be statement semicolon statement. Does it make sense?
New lines.
Sorry?
New lines.
The new line you can just ignore. You can have the tokenizer, the type 3 language, can just ignore the white space. When it finds white space, it just goes on. So S goes into space S. So the space is just ignored. Unless you want to build a language where white space is important. In that case, you should not ignore it. Okay? Other examples of statements that might be interesting to have? While loop, yes. So, while
Expression.
I would say expression actually. Do statement. Then we might want to have brackets statement if we want to prioritize. Well, we are missing a very important statement for if you have the while you have for.
Assignment.
Variable assignment, yes. So variable assignment. Variable assignment will be a variable ID. What is a variable ID? Basically, an identifier. And what's an identifier made up of? It is basically, so this is a type 3 parser. It begins with an underscore or a letter, followed by a bunch of underscores, letters, and digits. Okay? So we can always call upon another grammar, but some of them, like your variable ID, integer, etc., are the very simple ones that we can do all at once in Tokenizer. So variable ID is assigned to
Value.
expression. Okay? And the expression is a different color because I can.
Oh.
An expression goes into, as we saw before, expression plus expression, or expression times expression, etc. Or brackets expression, or integer, or yes. Are integer and bool type 2 languages? No, they're type 3. They are type 3 languages. Well, bool is actually quite a simple one. You either have a T is the first state, then R is the second, U is the third, E is the last one. Or F, and then you have another possible second state, which is A, then L, then S, then E. So int and bool is actually quite simple. Now, what other possible expression do we have?
Greater than, smaller than.
Sorry?
Expression greater than expression.
Oh, yes, but assume that it's here. So we have plus, times, greater than, different from, etc. What else are we missing? Sorry? Okay, assume that all possible constant values are here. Then come on. Are expressions always entirely made up? Sorry? Unless? Yeah, it's too much. Are expressions always made up entirely of constant values?
Oh, you can change them.
Yes, and when you change them, where do they go?
The variable ID.
Yes, a variable ID can come in an expression. Variable ID. Thanks to variable ID, what kind of expressions can I write?
X equals 1.
X equals 1, for example, x plus 3, etc. Okay? Very good. So, at this point, I would suggest take a short break. I know I have 20 minutes, and yet we are taking a 5 minute. Okay, guys. Guys, don't want to bother anyone with lecture, but Would also like it to resume. Imagine we want to build a program that given a list of tokens like integers, variables, IDs, booleans, etc. So these we have already read up somehow. So you can just do a scan of the file and build up the group the integers together, the variables ID together, etc. This is the job of the lexer. Now we want to build something that is capable of assembling a data structure that looks like one of our expressions. Right? So if we build this, if we translate this naively as an expr function, right? Then we might be tempted to write code that looks like the following. Let rec expr. Then we have a series of symbols. And then what do? We check if we can read an expr followed by a plus followed by an expr, right? So we could say, okay, let u1 is equal to expr of sim. Oh, sorry. u1 and sim1. So we get also the remaining symbols, right? Then we say, then guys, what's the next thing we expect?
Next symbol.
The plus. So we say symbol 1 must be equal to plus followed by symbol 2. Okay, it's kind of pseudocode at this point. And then we read the second operator, e2 equals e2, sorry, and e2 and sim3 is equal expr of sim2. Okay? What's the problem with this code? And it is a big one.
Requires every expression to have a plus. That'll be just value.
The first thing this function does is it calls expr on sim, which is the same thing as before. The next call, what's it going to do? Then the next one?
Yeah, it doesn't continue.
When does it stop?
When you shut the program
When at some point you say, oh, fuck it, there's a problem. Okay? So, we cannot translate this naively because we will get issues of infinite recursion. Which is a serious issue.
No.
No. So
Just build a bigger computer.
yeah, just build a bigger computer so you can recurse to infinity, but faster. A common strategy for dealing with this is to split the problem in two. Now, the issue of the code before is that it called exp on sim itself. If you eat up a character, then you are recursing on a problem that's smaller. But if you recurse on the very same list, then it's never going to end. So we always want to eat at least one character. So what we can do is imagine we find an expression such as 3 plus 5, sorry, 2 times 5 plus 1. Okay? We can separate parsing into two separate steps. The first one reads sequences of stuff according to the brackets. So we find the bracket, we recurse, so we get a list of symbols, and we expect that after the list of symbols, the remaining symbol is just a closed bracket. If we find a closed bracket, then we return no symbols. I will walk you through code that implements this. The point is that after this piece of code, after the first run through the code, what we have is we've separated. We have here a list of symbols, which is only one element within this list of symbols. So we basically build a tree of bracketized stuff. So our tree looks like 3 plus 2 times. So these are the elements of the outer list. So the elements are 3 plus 2 and times. We are not yet building the inner tree. And then one single thing, which is 5 plus 1. It's just one element here. Right? So this is because it makes sense. This is just an element in the prioritization, in the overall prioritization. Okay? So we have one list of either tokens or what is this? Yet another list of potentially tokens or other symbols. So this is a tree where one node of the tree contains a list of tokens, which are kind of leaves of the tree, or recursions into the tree itself. And this tree is built based on the brackets. So basically we had brackets here and brackets here. But we haven't yet done anything. We haven't yet done anything to merge, to combine the operators themselves. To combine the operators, what we can do is, at every level of the tree, we go through all the elements. First, we merge together which operators? The times or the plus? The times, because it's higher priority. So we go through the whole thing, we look for all the times, we ignore the additions. So we go through this, we find 3 plus 2. We look at the first 3 elements. 3 plus 2, do we do anything with it? No, we go on. Then we find 2 times. This is a single element so it sees it as a single element. Okay? So then what do we get? That we group this together. So we get a new list of 3 plus, and then here we have the expression times of 2, 5 plus 1. Then we go through this again. First element is 3 plus this. This is now a single object. And what do we create here? Just an addition. We create plus of 3 times 2 and 5 plus 1, which is a list. Then all the things that are not, that can still be reduced, you go through them. So now it's the turn of 5 plus 1. You look for all the multiplications in 5 plus 1, and you find how many? 0. Multiplications, times. So you find none, then you go through it again for the plus, and you find the 5 plus 1. And the final step is plus 5, 1. So the first step is you separate, you build sequences of stuff with respect to parentheses. The smallest sequence is 5 plus 1. That sequence is a sequence in itself, but a single element for the expression above, which makes perfect sense. So this is a single element in this multiplication. And then we have 3 plus 2 times, and this single element here. As long as we have stuff that needs to be compacted into an expression, we go through it. So for example, the 5 plus 1, it doesn't matter the order, we go through the 5 plus 1 once per operator in order of priority. So times has more priority, so we group together the multiplications. When we are done grouping together all the multiplications, we do another pass of the list where we group together the additions, and so on. And we do this with respect to these 3, compacting elements together in order of priority.
Does it predetermine which operators are in an expression beforehand? Or does it check all
You have done a pass
available?
with lexer, which tells you that this is int of 3, this is plus, so these are all objects that you build.
Yeah, but
This is
you don't
int
know
of
which
2.
You don't know which one one is going on top of the tree.
No, of course you don't.
No, it's not a standard.
No, you have no idea. You're gonna find it out later.
No, it's the middle one.
Yes. What I can offer you at this point, this is way too long and difficult to program in real time, so my apologies for that. What it can offer you is a simple implementation of a program that first takes a string of lists and gives you back a list of tokens. A token is, open bracket, an integer which contains a list of characters which make up the integer, or an ID, which is a variable name, which contains a list of characters. Then we have a close bracket, plus, times, end of file.
Isn't this something we have done?
Yes.
Oh, it don't make sense.
Here we have the Tokenizer function that, as you see, if it finds the space, a space or a tab, then it just goes on, it just ignores them. If we find plus, then we return the token plus, followed by the tokenization of the rest of the list.
What does /t do?
Sorry? This is the tab character. Tab.
Oh.
Yes. If we find the open bracket, the close bracket. So see, here we're not caring about whether or not the number of brackets is correct, etc. We find a bracket, we say, okay, here's a bracket. Right? We're just throwing away unsupported characters. If we find a digit, then we call another function tokenizing, which is another state, which is the state that will parse a sequence of integers, a sequence of digits. When we have the whole sequence of digits, which I call t in this case, I return int t, because int expects a list of characters, which are the characters that will make up the digit, and so on. Tokenizing is actually quite simple. As long as it finds, as long as it finds digits, then it keeps tokenizing integers. If it doesn't find a digit, then it goes back to tokenize. So when it's found the last digit, it goes back to the main tokenizer. The very same thing is done by tokenized IDs, so variable identifiers. If we recognize the first character, then we keep tokenizing an identifier. When we don't recognize it anymore, then we return an empty list of characters of the ID, because we are done with the characters of the ID, and we go back to the main tokenizer. The second thing we do is, from a list of tokens, because we get a list of tokens, which has no structure, it's just a sequence of tokens, we build a bracketized expression. So it is the same process I just showed on the smartboard. A bracketized expression is either a token or a sequence of bracketized expressions, or an expression, a whole expression, which is collapsed into a single element. And an expression is plus of two expressions, times of two expressions, a constant integer, or a variable string, or a variable ID, which is a string. Okay? So, I call this bracketized expression because it is a linear sequence of symbols. So this is a list of a bunch of symbols which in the beginning are all tokens. But as I find brackets, I create subsequences. Yes, this is a tree, but initially the tree has none of collapsed expressions, but it has very well a bunch of nested sequences. And we slowly merge every sequence into a merged expression. Now the code for this is actually not that long. If we find an open bracket, then we parse brackets with the rest of the string, and we expect that when we are done with parsing brackets, what we will find is a closed bracket. So basically, if we find an open bracket, we recurse, and the recursion goes on until it finds a closed. When it finds the closed one, this function doesn't do anything. It just leaves the closed bracket there. It says, no, a closed bracket, it's not my problem, it's the problem of who called me. And it says, I'm done. These are the symbols I found until the close bracket. And these are the symbols that remain, that I couldn't process. And what we expect is that in the symbols that remain, the first one is a closed bracket, which is the matching bracket of this one. And then we build a sequence with the rest, etc. Now, if we find a closed bracket, we give up. We stop immediately. We give an empty sequence, because if it's a closed bracket, then we have to notify whoever called us, which most likely was parse bracket itself, that we have found a closed bracket, so we stop. It's not our problem. If you find a closed bracket, you don't eat it. You give it back to who called you, because who called you might have seen the corresponding open bracket. So this is actually using the stack of the programming language with one stack frame per open bracket, which makes sense, because per open bracket you have to make sure that you find the corresponding closed bracket, but inside the open bracket you might have other open brackets. Alright?
Yeah, that was my question.
Oh, okay.
You don't know which closed bracket belongs to the open bracket.
Exactly.
Now you do.
No, you do. That's the point. So what this does basically is just eating up the brackets and putting together as a list of elements, as a sequence. So you see, when we find an open bracket, when we then find a closed bracket, we go on with the rest. We have parsed. We have here a sequence of things. We have here a sequence of other things, and this is a sequence of ES1 followed by ES2. So we actually put one after the other, which makes perfect sense. Yes, the rest is actually quite trivial. Here you have that whenever you find a token that is not a closed bracket and not an open bracket, then we convert it to an expression. So see, we check what the token was. If the token was an integer, then what is the type of X? No, not yet. It's a list of characters, because the tokenizer didn't worry about the content. It only guarantees this list of characters are all digits, are all valid. Yes, so it's telling us it's valid, but it's not telling us what the number is. Then here we parse the list of characters, or we create a string for the variable. Then the rest you'll be able to check yourselves. But this here is the function that collapses the tree. So whenever it finds a sequence, this is the key of all. First, it collapses the multiplications together. Then, it collapses the additions together. And you do first the multiplications, then the additions. And this is literally it. So after this is 116 lines of the whole tokenizer and parser for expressions, which I will put online if you want.
Yes, yeah.
Okay, then I will put it online. Okay, so as a wrap up, next lecture.